exactly behave in the same exact way that objects on the macroscopic level in classical mechanics behave. And as a result, there are things that we cannot actually understand, we cannot actually picture or actually visualize. And this eye is basically a testament to that idea. You can think of this eye as symbolizing the complexity of quantum mechanics, the complexity of nature, when we get down to the atomic and subatomic world. Now, the question is, how exactly is this equation useful? So this equation basically incorporates the great complexity of nature, of our universe, such as the quantum theory of energy, as well as the wave-particle duality of matter. Now, this equation, as we'll see in future lectures, explains a great multitude of natural phenomena, such as the production of unique light spectra produced by atoms. In fact, it explains in great detail why certain things take place in the line spectra of atoms. For example, why certain lines appear brighter than other lines. So, what exactly can we conclude from our discussion about this equation? So, the Schrödinger equation basically describes how our universe functions from the microscopic world to the macroscopic world. So, when we are dealing with very small things on the atomic and subatomic level, we basically use quantum mechanics to describe the motion of those systems and objects, and we describe them using the wave function. Now, the wave function itself can be obtained from the Schrödinger equation, and there are two forms of the Schrödinger equation. We have the time-dependent Schrödinger equation as well as the time-independent Schrödinger equation. Now, in the next lecture, we're going to show how we can use the one-dimensional time-dependent Schrödinger equation to basically solve for the one-dimensional time-independent Schrödinger equation. In the previous lecture, we discussed the time-dependent Schrödinger equation. Now, let's actually take this equation, let's solve this equation, and try to obtain the time-independent Schrödinger equation. So in this lecture, our goal will be to obtain the time-independent Schrödinger equation from the more general time-dependent Schrödinger equation given by equation A. So, this is the one-dimensional time-dependent Schrödinger equation. One-dimensional simply means our object on the atomic or subatomic level is basically moving along one dimension. Let's suppose along the x-axis. So, notice in this equation we have the left and the right side. So, the left side is equal to the right side. On the left side, we have the partial derivative of the wave function with respect to time when x is held constant, and the right side of our equation has the second partial derivative of the wave function with respect to the position along the x-axis when time is held constant. And we also have the single wave function term, which is basically a function with respect to x and with respect to time. Now, let's begin with step 1. So the goal is to basically somehow take this equation, try to solve it, and obtain the time-independent Schrödinger equation. So basically, we have to use some type of trick. So let's begin with step 1. So sometimes in mathematics, if we have a function that is a function of two variables, we can take that function and express it as a product of two different functions that themselves are functions of a single variable. Now, what exactly do we mean by that? So hypothetically speaking, let's suppose our function is given by f, and that function is a function of two variables x and y. So fx comma y. Now, what we mean by this statement is the following. Sometimes in mathematics, we can take this function and we can represent it in terms of the product of two different functions, g and h, for example, where g is a function of variable x and h is a function of variable y. So sometimes this is true. Now, in quantum mechanics, this is also sometimes true. So let's examine our wave function. The wave function is in fact an equation. It's a function that is a function of two different variables. In this case, our y is replaced with the time. So we see that our psi, capital Psi, is with respect to x and time. So that means sometimes it must be true that this is equal to the product of two different functions, where this is lowercase I, and lowercase I is a function of simply x, and f is a function of simply t. So f is independent of x, and lowercase I is independent of t. So let's call this equation B. So we have uppercase psi x comma t is equal to lowercase psi of x multiplied by f of t. So now let's take equation A, and let us now substitute equation B into equation A. So if lowercase psi is equal to x comma t, so that means we can replace this, we can replace this, and we can replace this with the product of these two independent functions. So that's exactly what we get in the following step, in step 2. So by taking equation B and plugging into equation A, we get the following equation. So the left side becomes as follows, and the right side becomes as follows. Now let's move on to step 3. So now we take the following equation, and we divide both sides by lowercase psi with respect to x multiplied by f with respect to t. So the purpose of that is because we want to basically separate our variables. We want to take one variable and place it on the left side, and the second variable and place it on the right side. So that will become important, as we'll see just a moment. So we divide the left side by this term and the right side by this term, and we get the following result. So we have I multiplied by h bar multiplied by 1 divided by f of t multiplied by the partial derivative of our f with respect to time. And this is equal to, notice that this quantity will cancel, because when we divide this side by this quantity, this will cancel entirely, and we'll simply left with u with respect to x, where u is simply the potential energy of our particle, and it depends on the position x with respect to the one-dimensional axis, the x-axis. And we subtract this. So notice the f of t term will cancel, because this partial derivative does not depend on t, it only depends on x. So this term will have, well, we have h bar squared multiplied by k squared divided by 2 and multiplied by 1 divided by our lowercase psi time of x multiplied by the second partial derivative of our lowercase I with respect to x. So, once again, in mathematics, this procedure is known as the separation of variables. We basically want to separate the variables. One appears on the left side, the second one appears on the right side. So, in this equation, we see the t term appears only on the left side, and the x term only appears on the right side. So, once again, notice that the left side is strictly in terms of time as well as other constants, while the right side is strictly in terms of position, and once again, in terms of other constants. Now, why exactly is that important? Well, notice that the left side is equal to the right side. Now, let's look at the right side. The right side only really depends on the position given by x. Now, when x changes, that means the right side also changes because the right side depends on x. But when x changes, that doesn't really mean that the left side will change because the left side does not actually depend on x. And likewise, if the time changes, the left side will change, but the right side will not necessarily change. However, according to this equation, we know that the left side must equal to the right side. And the only time that this is actually true is when the left side is equal to the right side is equal to some constant. So, this basically implies that both sides must be equal to some constant. Let's call this constant e, and we'll see why that's important in just a moment. We can call this constant some other constant, for example, a, b, c. So, we basically take the left side of the equation and we set it equal to our constant e. We take the right side of our equation and we set it equal to our constant e. So, this is equal to this side. So, let's call this entire equation equation c. So, let's take equation c and now multiply both sides of that equation by lowercase I with respect to x. So, our wave function, that only depends on x. So, if we multiply the left side, we get this quantity. If we multiply the right side, we get this quantity. And notice, this is exactly the one-dimensional, non-relativistic, time-independent Schrodinger equation. So we see that we can readily obtain the time-independent Schrodinger equation from the more general time-dependent Schrodinger equation. So we were able to solve this equation and we obtain the time-independent Schrodinger equation. In this lecture, we're going to basically begin from where we left off in the previous lecture. So let's review what we did in the previous lecture. So previously, we basically took the general form of the Schrodinger equation, also known as the time-dependent Schrodinger equation, and we basically followed a few steps, and we ended up with the time-independent Schrodinger equation. So what exactly is the difference between these two equations? So in this equation, our wave function, also known as the total wave function, depends not only on the position x along the x-axis, but also on the time. Whereas in this equation, the time-independent Schrodinger equation, our wave function, only depends on x and does not depend on time. So in this case, the time is fixed. So what we basically did is we used the following mathematical relationship. We took this and plugged it into our general form of the Schrodinger equation. Then we divided both sides by this quantity, and we separated the variables so that the left side has one variable and the right side has a second variable. And then we ended up with the following two equations, where e is simply some arbitrary constant. Now, if you're not certain what I just said, go back to the previous lecture and review what we did in that lecture. Review what we did specifically to get from this general form to this specific case. So in the previous lecture, we basically focused on the following equation. So we took this equation, we multiplied the left and right side by our side with respect to x, this quantity, and we ended up with this equation. But in this lecture, our focus will shift onto the following equation. So e, our arbitrary constant, is equal to I multiplied by h bar, multiplied by 1 divided by f of t, multiplied by our derivative of f of t with respect to time. Now, what exactly will be the focus of this lecture? What will be our goal? So we basically want to take the following equation, which we're going to label as equation A, and we're going to solve this equation. We're going to try to determine an equation for the total wave function in terms of our wave function. So we want to determine our equation for psi x comma t with respect to only lowercase I x. So this is uppercase I, by the way, and this is lowercase I. We use uppercase and lowercase to distinguish between the total wave function and our wave function that appears in a time-independent Schrodinger equation. So let's begin with step 1. We basically have 4 steps that we're going to follow to determine an equation for our total wave function with respect to our wave function. So let's begin with equation A, and let's take equation A and let's rearrange equation A as follows. So the left side, we have d f of t divided by f of t is equal to e multiplied by dt divided by I multiplied by h bar. dt is also an infinitely small quantity. So we can now basically integrate both of these sides. If we integrate the left side, we get natural log of f of t. If we integrate the right side, we get negative I multiplied by e divided by h bar, and this dt simply becomes t. So now let's take this equation and move on to step 3. So now we basically want to take the exponential of the left and right sides. So if we take the exponential of the left side, we get the following result, e to the power of natural log f of t. And if we take the exponential of the right side, we get the following result. Now notice that the exponential e to the power of ln is simply f of t. So we see that f of t is equal to e to to the power of negative I multiplied by E multiplied by T divided by H bar. So now we are ready to go back to the following equation and replace f of t with the following result. So remember, our goal was to basically take the total wave function that appears in the general form of the Schrodinger equation and represent it using our wave function that appears in the time-independent Schrodinger equation. So we basically take this equation and we plug in this exponential quantity into the following f of t. So we see that the total wave function that depends on position and time is equal to the wave function that only depends on the position that appears in the time-independent equation multiplied by f of t, which is equal to this quantity e to the power of negative I multiplied by e times t divided by h bar. So what exactly is the meaning of this equation? So let's try to interpret what this equation actually means. So we basically determine the equation for the wave function that depends on position and time in terms of the wave function that only depends on the position and does not depend on the time. Now, the question is, what is the meaning behind this equation? Well, what is the wave function? The wave function basically gives us a way that we can represent the motion and behavior of any object on the atomic and subatomic level in quantum mechanics, such as, for example, an electron. So when an electron moves along the x-axis, we can describe the motion and behavior of that electron as it moves by using this equation. Now, notice that this equation has a negative I term. It has an I. And what exactly is the I? Well, the I is basically an imaginary number. It's a number that does not actually exist. So we can't simply say, for example, that we have I number of markers because I is a number that doesn't exist. We can say we have 1, 2, 3, 4 number of markers, but we can't say we have I number of markers. So that basically means I is not a real number in the sense that it is not physically measurable. We can't actually visualize what the number I means. And because I appears on the right side of this equation, that means we cannot actually measure what the wave function is. So our wave function in this term, in this form, is not actually physically measurable. It's not actually physically meaningful. So if we somehow take this function, we play around with it, and we get rid of the negative I, well, in that case, that will produce some type of value that is, in fact, physically measurable. Now, what we can do is we can take the square of the absolute value of both sides. So if we take the square of the absolute value of the left side, that means we have to take the square of the absolute value of the right side, and that's exactly what we do. Now, notice, the absolute value of e to the negative I e t divided by h bar is simply equal to 1, and 1 raised to the power of 2 is equal to 1. So this quantity disappears, and we see that the square of the absolute value of the total wave function that depends on position and time, that appears in the general form of the Schrodinger equation, the time-dependent equation, is equal to the square of the absolute value of the wave function that only depends on x and does not depend on time. So this is what appears in a time-independent Schrodinger equation. So what exactly is the importance of this? What is the meaning behind this physically measurable, physically meaningful value? Notice that now we're not dealing with any imaginary term, and that means this value is actually physically measurable. We can actually quantify what this value means. So this, as it turns out, basically represents the probability of finding our electron along any position along the x-axis. So this is known as the probability density of our particle. Now notice, because this is the same exact thing as this, and the right side of our equation does not actually depend on time, that means the probability density of our electron, our particle in space, does not actually depend on time. So what exactly is the meaning behind this idea? So let's suppose we have the following region of space. So notice we're dealing with a two-dimensional region in space. So let's suppose that we know that the probability of finding an electron in this region is basically 20%. So we calculate this, and the probability of finding an electron in this region is 20%. So what exactly does this statement mean? So because this is equal to this, and this does not depend on our time, that basically means it doesn't matter what the time is, our probability of finding the electron in this region of space will always be the same. It will always be 20%. So basically, it doesn't mean if we check now or in an hour, the probability of finding that electron in that region will always be 20%. That's exactly what we mean by the following statement. So let's review what we just discussed. So in the previous lecture, we basically used the general form of the Schrodinger equation known as the time-dependent equation to solve for the time-independent equation. And in this lecture, we basically used equation A to determine what the probability density is. The probability density is basically given by the following equation. You can take this and square it and square the absolute value. That gives us the probability density. In this lecture, we're going to discuss a concept in quantum mechanics known as the plane wave. Now, before we define what a plane wave is, we must understand what a free particle is. So in quantum mechanics, we define a free particle as a particle that does not actually feel any outside force. And because it doesn't feel any force, the potential energy of our free particle does not actually change. And so we can arbitrarily choose the potential energy of a free particle to equal to 0. So let's suppose we have a free particle, let's suppose an electron that is moving along the x-axis in the positive direction. So the potential energy of the electron is arbitrarily chosen to be 0. Now, how exactly do we describe the motion of this electron as it moves along the x-axis at any fixed instant in time? So we can describe it using the time-independent Schrodinger equation that is given by this formula. So the product of the potential energy of our free particle and the wave function that describes the free particle minus this constant multiplied by the second derivative of our wave function with respect to our x position is equal to the total energy E of our free particle multiplied by the wave function. So once again, recall that this time-independent Schrodinger equation uses the wave function given by psi with respect to x, and the wave function actually describes the motion and behavior of our free particle, our electron. So basically, we can use this equation to solve for the wave function. Now, because we're dealing with a free particle and we arbitrarily chose the potential energy of our particle, the electron, to be zero, this quantity is zero. And if this quantity is zero, this entire quantity is also zero. So we have negative this is equal to this. Now, if we multiply both sides by 2m and we divide both sides by h bar squared and bring this term to the right side of our equation and set it equal to zero, we get equation A. So the second derivative of the wave function with respect to x plus this constant multiplied by the wave function is equal to zero. Now, notice what this equation actually looks like. So we call the equation of motion for simple harmonic oscillators in classical mechanics. It looks something like this. And this is actually very similar to equation A. In fact, by analogy to equation of motion of simple harmonic oscillators, we can readily show that the solution to equation A looks something like this, which is similar to the solution for this equation in classical mechanics. Let's call our solution equation B. So basically, if we replace these two quantities with this equation, these two sums will equal to zero. That's exactly what we mean by solution to equation A. Now, what exactly is this K term? Notice in the equation of motion for simple harmonic oscillators, the K is the spring stiffness constant, but the K in this equation is not the spring stiffness constant. The question is, what exactly is our K? So from the conservation of energy, we see that the total energy of our free particle electron, E, is equal to the sum of the potential energy and our kinetic energy. Now, the non-relativistic kinetic energy equation is 1/2 mv squared. Now, because our momentum is equal to mass times velocity, and from this equation we see that the velocity is equal to the momentum divided by the mass, we can replace this velocity with p divided by m, and we get this result. So E is equal to u plus p squared divided by 2m. But because we're dealing with a free particle, our u is simply equal to 0, so E is equal to p squared divided by 2m. Now, recall that the momentum is also related to our k by the following equation. So the momentum of our free particle is equal to the product of k and h bar. So this equation was discussed in the lecture on the time-independent Schrodinger equation. So if you're not certain where this equation comes from, go back and watch that lecture. So basically, if we take this p and replace the p with this product, we get the following result. So E is equal to h bar squared multiplied by k squared divided by 2 multiplied by m. Now, if we solve for k using this equation, we see that k is equal to the square root of 2 multiplied by m multiplied by E divided by h bar squared. So this is what our k is. Once again, the k is not the spring stiffness constant that we spoke about in the equation of motion for simple harmonic oscillators in classical mechanics. So, what exactly can we actually conclude from this discussion? What exactly is the plane wave? Well, if we have a free particle that is moving along the x-axis along one dimension with the momentum given by p and the total energy given by E, we can represent that motion of that free particle by using a sinusoidal wave, and this sinusoidal wave is known as the plane wave. So once again, if we look at the following equation, and if we examine our solution to equation A given by equation B, we see that the motion of our particle is sinusoidal, and this is known as the plane wave. In fact, if we look at equation B and we take our constant p and set it equal to 0, then the solution to this equation A simply becomes as follows. So by the way, A and B are simply some complex constants. So if we set B equal to 0, then the solution, our wave function with respect to x, is equal to A multiplied by sine of k multiplied by x, where k is this quantity. Now, if we take this and we plot it on the xy axis, where the x-axis is our position given by x, and the y-axis is our wave function given by sine with respect to x, we get the following sinusoidal wave, where A is simply the magnitude, the amplitude of our wave. So this is known as a plane wave. So once again, basically, a plane wave is produced by a free particle that is moving with a momentum m and an rp and an energy E. Now, notice, because we're dealing with quantum mechanics, and because we know precisely what the momentum p is by the uncertainty principle, if we know what the momentum p is precisely at any given moment in time, we can't actually determine where our particle is, because the uncertainty in our position is infinitely large. So once again, notice that p, our momentum, is precisely given, so the change in p is 0. Therefore, there is no way of knowing the position of our free particle, because the delta x, the uncertainty in x, from the uncertainty principle, is infinitely large. So that means if we know what the momentum is of our particle, we actually have no way of telling where our particle is found along the x-axis. If we have anywhere along the x-axis, our change in x, our uncertainty in x, is infinitely large. Now, in the next lecture, we're actually going to look at a specific example that deals with the plane wave. In the previous lecture, we discussed the particles and waves that those particles produce, which are known as plane waves. Now let's look at the following example that deals with free particles and plane waves. So let's suppose the free particle, the electron, is moving along the x-axis in the positive direction with a total energy of 10 electron volts. Now, if we make the assumption that the potential energy of our free particle is 0, in part A, we want to determine the wavelength of the plane wave produced by the free particle, and in part B, we want to determine the wave function that represents the plane wave that was produced by our free particle. We're going to assume that our constant B is equal to 0. So let's begin with part A. So in part A, we basically want to calculate the distance between any two consecutive crests of the plane wave that is produced by the free particle. And to do this, we're going to use equations 1 and equations 2 that we spoke about in the previous lecture. So K, our constant, is either equal to 2 pi divided by lambda, or it's equal to the square root of 2m e divided by h bar squared. So basically, to calculate what our lambda is, knowing the mass and our energy, we can take these two equations, set them equal to one another, so that the K will cancel out, and then we can solve for our lambda. So setting equations 1 equal to equation 2, we get the following result. Next, we rearrange and solve for our lambda, and the wavelength is equal to 2 pi divided by the square root of 2m multiplied multiplied by E divided by h bar squared. Now our energy is given in electron volts. So to use the energy, we have to convert the energy from electron volts to joules. And to do that, we have to multiply 10 by 1.6 times 10 to negative 19 joules. Now M is the mass of our particle. Because we have an electron, the mass of the electron is 9.11 times 10 to negative 31 kilograms. And we also need the quantity that represents h bar, and that is equal to 1.055 times 10 to negative 34 joules multiplied by second. So we plug in those values into this equation, and we get that the wavelength of our plane wave produced by the free particle is equal to 3.89 times 10 to negative 10 meters. So this is the distance between any two consecutive crests of our sinusoidal plane wave. Now let's move on to part B. In part B, we want to determine the wave function that represents the plane wave produced by our free particle. So we're assuming B, our constant, that appears in the wave function equation is equal to 0. So in the previous lecture, we basically said that the equation for the wave function of our plane wave is given by this formula, where A and B are two constants, and K is given by equations 1 or equations 2, and X is our variable. So basically, we know that B is equal to 0, so the second term cancels out, and A is simply an unknown constant that we cannot solve. So we're going to leave that as it is. But we can solve for K. So we can use equation 1 to solve for K. K is equal to 2 pi divided by lambda. The lambda is equal to 1, so we plug that in, and we see that K is equal to now 1.62 times 10 to the positive 10. So now we can take this equation and rewrite it in the following form. So the equation that represents the wave function of the free particle is equal to A multiplied by sine of 1.62 times 10 to the 10 of x, where x is simply our position along the x-axis. So if we can, if we want to, we can actually plot this on the xy axis, where the x-axis is simply our position of the free particle along the horizontal axis, and the y-axis represents our sine of x. It represents our wave function. So it looks something like this. And the distance between any two consecutive crests, the distance between, say, this crest and this crest of our plane wave produced by the free particle is given by 3.89 times 10 to negative 10 meters. In quantum mechanics, whenever a free particle that has no potential energy is moving along some horizontal axis, along some dimension, the wave